afternoon, everyone. It's really awesome to be back in Victoria giving a talk. I remember when I was last living in Australia, I didn't actually go to YOW or any of the talks here because I know at the time I have a distinct memory of thinking of myself as like one of the people who don't go to conferences. Like I didn't feel like I was kind of part of the act, part of the conversation. And I certainly didn't imagine speaking, so it's really good to be here and able to do this. And I'd say to anyone who's considering speaking, please bear in mind that the way that kind of we earn our place on the stage is not by necessarily knowing the most about a topic or being virtuoso at it. It's just by taking the time to organize content and put in the practice. So if you are thinking of it, please give it a go. So this talk is not exactly about programming. I know you've come to a programming conference, so that's probably the main point of interest. But this is going to use programming not as the actual artwork itself, but as the medium, the means of expression, the instrument. This talk is actually about music. And I think that's okay because as an industry, we're quite solipsistic, right? Programming conferences are about programming. Like writing, not all film festivals are films about films, right? Some of them are perhaps, and they can be very good. But every now and again, it would be nice to look outward, especially as software comes to influence so much of the world. We need to think about not just about the software itself, but what that can teach us about other things. So I said that I'd talk about music, and this is what many people mean when they talk about music in a certain context. So this is a piece of Bach, and it's written in Western music notation. So the secret to understanding this, if you don't already, is that each dot is a note, and the way that you know when that note is played is where it is on the horizontal axis, and how you know how high that note is how high it is on the vertical axis. So it's a kind of a specialized graph. And I'll make the claim that this Western music notation, this way of not so much being music, but of describing music, I make the claim that it's a regular language in the sense of regular expression. Because there is no nested stack. There is no set of procedures that you have to unravel to execute it at runtime, right? It's optimized for being played one note at a time. And that's because like a regular language, other regular languages, it's designed to be executed on a peculiar kind of finite state machine called a musician, right? So if you're up stage and you're playing away on your instrument, and you're wondering what happens next, you don't have the time to walk through a whole kind of stack trace of procedures to know what note you want to play next. You have to know immediately what it is. So it's a format that is really well designed for its purpose, but its purpose is around performance. And that means that there are other kinds of structure present in music that this notation is not optimized to reveal. So one bit of structure that I'll talk about very briefly now is canonical structure, where a canon by Bach or anyone else is where you have one melody, like this one you can see here, this kind of mountain range, and then you have another copy of it that is somehow a transformation of it. So if you look carefully, you'll see that there's, follow where I'm doing the mouse, there's this mountain range here, and then there's a mirror image of it that happens down here later on. So they're the same notes, but transformed. So that's not something that's directly visible in the notation. And I've picked this, I guess, because this is, as far as Western music notation goes, this is a kind of structure that's about as visible as it gets. But the nice thing about programming music is we can create abstractions that fit the specific domain we're talking about, which could be a genre of music, it could even be a piece of music. Like when you write your own applications, you design classes, subroutines, functions, whatever, that map to your specific problem. Not all code is framework code. So what I'm going to do is I'm going to walk back up to this piece of music by showing you how it's built in code. So throughout this talk, I'll be relying on executing commands against a Clojure REPL from Vim, and I'll be using the Overtone audio environment, which was written by Jeff Rose and Sam Aaron, who happens to be sitting here today. Right, so the most basic thing you might know already about music is that sound is made of sine waves. So it's not the same sine wave as the ocean. It's not the waves going up and down. Actually, what happens when you have a sound wave is you end up with these little signals traveling transversely along the medium. So the molecules are actually moving between me and you as I talk. So what we're actually getting is a pressure wave. So there's periodic high and low pressure, and that oscillates at a certain frequency, and that frequency determines how high the sound we hear is. So I'm going to play a tone that's oscillating 300 times a second. All right, whoops, stop that. All right, so if I played it at, maybe just lower the sound before I do this. If I played at 200 hertz, it would sound lower. Played, let's try 50 hertz. That's even lower. Right? And the amplitude of the wave is how loud it is. But so far, what I've actually been doing when I executed those commands was killing it manually. Right? So that tone, a sine wave by its nature, goes on forever. But in music, that's not what happens, right? We need events. We need it to happen in a discrete period of time, then move on to another note. So what I've got here is an instrument that takes both a frequency and a duration. And the innovation that it has relative to the first example is that it creates what's called an envelope on this line. So an envelope controls the amplitude of the sound. So it starts at 1. Whoops. It starts at 1, and then it goes to 0 over duration. So it has the effect of the sound fading out, so we can make a note. So you don't have to believe me that's what the Clojure says, especially if you don't read Lisp, because this is what it sounds like. So it fades out, right? So we're starting to build up abstractions, right? We've started with this sine wave, and now we have a chunk of sine wave that occurs at a particular period of time, or for a particular period of time. The next thing I need to explain, I'll need to rely back on the slinky again, is how we make the sound more realistic. So the sound waves might not go up and down, but the string of a violin or a guitar or whatever else does, right? It oscillates like this. So what determines the sound, the frequency you play when you pluck it, is the resonant frequency. So you can kind of imagine this loop, if you look at the outline of what I'm doing, as a sine wave that's wrapping around itself and crossing the x-axis at my hand. So that's the frequency that can survive as this string vibrates. But you might say, well, why this exact frequency? Why not double this? Because that would also cross the x-axis at where my hands are. So it actually turns out that you can do that, right? So a slinky or a string will oscillate at double the base frequency if you push it in the right way. So the reason that's important is that realistic sources of sound aren't a single sine wave. They're a whole harmonic progression of the base frequency and then double the base frequency, triple, quadruple, etc. The higher ones are softer, so they kind of die out, but it's the combination of these sound waves that makes the sound that you hear. So with this bell, you don't need to read the details, but what I'm doing is combining together that harmonic progression to make an instrument I've called the bell, where I can control the relative volume of all the harmonics. So if we listen to the beep again, and then the bell, right, the bell is much more realistic. It's fuller sound. But we can do better than that because one of the things that makes real physical instruments interesting is that they're not platonic ideals. They have imperfections and idiosyncrasies that make them special. So actually, with a case of a bell, rather than the pure harmonic series that I indicated, a bell, actually, its higher harmonics are a bit higher than the ideal model would suggest, just to do with the shape of the bell. So if I reevaluate the code and play that bell again, it sounds even more realistic, right? I'm taking advantage of the fact that I've got some really nice low speakers provided by Jed and Rick. Let's try 50 hertz, that's probably about the minimum of reasonable. Yeah, I'm normally not able to do that, so thanks, Rick. So now we've got a bell, we've got more realistic sound, but we've still got a long way to go to get to the full Bach canon. One point I do want to make in passing is that as with any signal, the processor of the signal is a really important part of what gives it meaning. So your mind, your ears, are not passive recipients of the sound. You're reconstructing what you expect in all sorts of interesting ways. So to make that point, I'm going to show you a kind of an interesting factor of psychoacoustics, the psychology of processing sound. So if I play 3 bell sounds that are 600, high, 500, and 400 hertz, high, medium, low, the interesting thing about this is that if you look at the 500 hertz bell, I've actually overridden the bass frequency to have a volume of 0. So the bass frequency of that bell has been cut out altogether. And if you look at the 400 hertz, I've cut out both the 0th and the first harmonic. So in practice, the lowest sound here is 600 hertz. The lowest frequency in this bell is 1,000 hertz. And the lowest one here is actually 1,200. But you hear them as low, medium, high, despite numerically you might think the other way around. The reason for this is that the harmonic progression is something that your brain has evolved to be aware of. So if your brain sees a sound composed of 400, 300, 200 hertz, it implies that there should have been a 100 hertz there and it's able to error correct. And that can be important, for example, if you're listening to someone's voice on a really small speaker. You probably can't actually hear the frequency of their voice, especially if they've got a deep voice, but you can reconstruct it. So moving on. So far, we've talked about the continuous frequency spectrum. Everywhere from like 0 hertz to 20,000 hertz is equally valid according to the model I've given so far. So music isn't like that. Music, some things are in tune, some things are out of tune. And the thing that governs that is that actually music is in some sense digital, in a pedantic sense, that this instrument has a button. It chooses a subset of the available frequency spectrum to play. So what governs what plays those, what notes are included? Well, in most musical cultures, doubling the frequency of a sound is a kind of equivalence relation. So you'd hear it as a different sound, but somehow as equivalent, like Monday this week, Monday next week. So if I play, and then, it's the same melody, right? But it was double the frequency. But you could hear it as equivalent. So if we start with that as our base model, then we've actually got 12 jumps in between one note and its double. So the way that frequencies work is via a ratio system. It's not absolute, it's relative. So each jump is increasing the frequency by the 12th root of 2. Right? There are other tuning systems are available, but this is the one that dominates Western music now, so I'll stick with that. Look on Wikipedia if you want to find more interesting ways of doing it. So we can easily model that. We can write some code to mathematically model it, just do some arithmetic using Java, and that lets us express things a bit closer to the domain. So 440 hertz is concert A. That's the standard, I guess, that orchestras tune against. That's almost 440 hertz, right? Close enough that I don't think there's anyone who's a good enough musician that would be able to hear that difference. So if we give it 70, that's 440 hertz times the 12th root of 2. So we can easily do that calculation. And by doing that, we can express the music not in raw frequencies, but by numbering the keys of the music we want to play. So we're getting closer and closer to the domain. I think probably to make it a little bit easier, we've defined an instrument here, or not, it's actually a function this time, that will take that higher order MIDI note and it'll ding the bell using our conversion from MIDI to hertz. So now we can start playing things. Whoops. In the MIDI. But still we haven't talked about the time domain. We've only really talked about pitch. So this is kind of a micro framework I'm going to use to express the final product. You don't really need much more than this. The thing to maybe that I should step you through is this play function. So this play function takes a sequence of notes. What's a note? Well, a note is, if you look up here, it's a pair of time and pitch. So those dots, when we look at Bach, they're also time-pitch pairs, but expressed in a visual way. So what play does, it takes a sequence of notes. It takes these notes, and it says, give me these notes where the time element of these notes is offset from now. So rather than playing from 0, which I guess would be the beginning of the Unix epoch in 1970, shift them to the present. And then do seek, which is kind of Clojure's for each. for each millisecond time in MIDI pitch in the scheduled notes, at that milliseconds, ding the bell. So it's just a function that takes a pure data structure, a sequence of time-pitch pairs, and turns them into a side effect. But because this is functional programming, that's convenient because we can do all sorts of calculations on the pure data structure without having to worry about composing side effects. So here's what happens if I play the notes from 70 to 81 as a MIDI. Cool. So all I've done is I've spaced each note with a third of a second. Now I'll play that again, and I think it sounds kind of interesting, but it doesn't sound like something that you'd hear in a real piece of music. Right? And the reason for that is there's still a layer of abstraction that I haven't talked about yet. We need to go higher. So the layer of abstraction that would really make this start to sound like a real piece of music is called scale. So maybe it's easy to demonstrate what maybe the major scale is. So if you look back at the physical instrument, you can see even though all the buttons play a note, some of the buttons are red, they'd be black on a real piano, and some of the buttons are black, they'd be the white keys on a piano. So what that means is that in a piece that is in the major key, C major specifically, we would play the black notes, and for this piece specifically, we'd ignore the red notes. We'd choose this black note subset. So rather than going, we would go, so we're choosing that subset, and different keys might be chosen for different effects or relative to other keys in an album or something like that. So again, we can express that really nicely in functional programming. So what major is a function that we've built out of scale. So it knows that there's a double jump up to between this black note and the next note for the first note of the major scale, then a double jump, then a single, double, 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 single. So we've captured that pattern visibly in our code. That's what a major key is made of. So all we need is that major is a function, a very simple function that takes a position in the scale, whether it's the 0th note of the scale, the first note, and tells us what MIDI to hit from. But we don't really want to start from 0. We want to start from, I guess, this is C. And if we start from a different point, the relative relationships are the same. But that was in D. And the difference is the offset. So it's where your starting point. So C, in the sense of C major, could be seen as a function that just adds 60 to everything. Right? It just pulls you up from 0 on the axis and translates you to the point in the scale you want to start. So the nice thing about that is if you want to express keys, you can just use the functional composition operator. So this is C sharp major. So the major, it converts from a position on the scale to the MIDI, and the C sharp works out where our starting point is. But we're not using, like comp is not a special function, that's just ordinary function composition. So that's a C major scale. And if we want to substitute that, we don't need to change our melody. We can just start plugging together different functions. So here's D sharp major. Here's D sharp minor. Ooh, that sounds much like sadder, much more intense, right? But the only difference, if we go up as how minor is defined, is that the pattern of big and small jumps is in a different order. So it's the same big and small jumps, but you can see visibly that the difference is the first one is a double jump, like ordinarily, but in a minor key, the second one is the single jump. So we can compose different scales just by defining what happens between one note and the next. So let's try, E blues. Right? That sounds different, right? It evokes something different, and it's just by grouping different big and small jumps that are all made out of the 12th root of 2. Let's listen to the E pentatonic scale. Right? It has a different connotation. It sounds like East Asian music, right? That's because that scale is associated with that music. what I quite like is that the blues scale and the pentatonic scale are mathematically very similar, even though musically they have very different associations. The difference is that the blues scale has one extra note in it. So there's a double jump in the pentatonic. There's 2 single jumps in the blues scale. So that's all it takes to give that dramatically different feeling. It is not obviously the case that they are, that the blues scale is mathematically sadder than the pentatonic scale, of course, right? Just to caution. But you laugh, but throughout a lot of history, musicologists have tried to figure out, with their perspective of Western European music as kind of objective reality, they've tried to explain, well, why is this key mean this and this other kind of key mean something else? Why is minor sad? But I think it's a little bit futile because the real reason is just the cultural associations, that minor key is sad because you've heard a lot of sad music while watching a lot of sad movies in the minor key. Right? So I'm not trying to say it's objective. Again, it's the receiver of the signal that goes a long way to defining what it is. Right, so we've talked about when notes happen, and we've also talked about our system for decoding from everything from a position in the scale all the way back down to frequency. So it's now time to start talking about melodies, sequences of notes that have times and pitches. So this is a way, not in any way the best way or the only way, to write row, row, row your boat. This is kind of the simplest way I could think of, given that I've shown you all the code for this micro framework on screen so far. So the way it works is the pitches are here. So row, row, row your boat. We've numbered them out, right? And the timing, much less robotic than me, obviously, are down here. So we've got durations and pitches. There's probably much more interesting ways to notate music, and perhaps there's an interesting way that fits your particular piece of music. You don't have to design a universal notation because everything compiles down in the same way. So we just do a little bit of functional programming magic, and we end up with something that looks like this. Right, so not really in itself very interesting, but we're starting to build up quite large bundles of notes. Looks a lot like JSON. That's what Clojure data structures look like. But this is something that our play function knows very much how to handle because it can see at all points where the time is, where the pitch is. Oops. Cool. Now, there's a lot of symmetry in music, at least at first approximation, between things that happen in the pitch space and things that happen in the time space, as you might expect if you think about it as a graph. Right? They're kind of fundamentally similar things mathematically. So in order to control the time and the pitch of row, row, row your boat, or rather the tempo and the key, we just need to apply functions, one to the time of each note and one to the pitch of each note. So what this little bit says here, it says take all those raw melodies where the time key is being multiplied by this beats per minute 90 function, which just scales it, and where the pitch has been multiplied by the C major function, which we know from earlier controls the pattern of big and small jumps and shifts it to a start at a certain point. So it sounds like this. Right? And if we decide we want a different tempo or a different key, we don't need to change the original melody. We can just change the functions we're applying to the time and pitch pairs. We've kind of separated our concerns. All right, so far everything I've showed you is to some extent not so much universal, but certainly not specific to a certain genre of music. It's all been pretty generic, mostly Western European music. But I promised that we could create abstractions that suited a particular piece. So we're starting to get a little bit more complex code because it's a little bit more specific, less universal. But rather than show you how this run function works, I can show you what it does. So what run does is it takes advantage of the structure of Bach's kind of music where there are a lot of notes that are adjacent. So you can see these melodies, there are discontinuities, but they're kind of mountain ranges where they have this smooth curve. So there's a bit of structure in there we should be able to exploit so that we can be A, more terse in our code, and B, so we can convey the intent or reveal structure in the music. So what this run does is takes the mountains and the valleys and just joins them together in integers. Right? And the reason I want to do that is, well, if you think of Bach describing one of these pieces of music, he wouldn't say, oh, you know that bit where it goes, G, A, B, C, D, E, F, G, A, right? He wouldn't express it that way in the literal notes. What he would say is, well, you know that bit where there's a run from G up to the higher A? So if we're able to create functions that allow us to talk in those higher level concepts, we're getting, again, closer to the domain, which has the advantage of making any changes that we need to do in the domain, like changes in key, small to changes in our implementation. And in music also has the other benefit that your mistakes sound good, right? Because your mistakes make sense. They're variations rather than fundamentally clashing, which is a very useful attribute when doing live performance. So this melody here, this whole big paragraph, is quite a lot of complexity, and there's probably nicer ways to design notations to do it. But this is equivalent to, well, actually a lot more than this piece of music here. Right? We've got to the point where using our runs, using the fact that the music has peaks and troughs, it allows us to, in a reasonably terse way, express what is quite a lot of music. I'm not actually sure where we've notated up to, but it's quite a lot. Whoops, sorry about that. But before I play the actual Bach piece, I want to talk about that canonic structure that I mentioned, because we haven't come to that yet, and that's a really interesting part. So, a canon is defined pretty well, I think, by the code here, and I hope that if you haven't seen Lisp, it still somewhat makes sense. This says a canon is a function that takes a function f and some notes and returns the notes accompanied by a functional transformation of themselves. So it's a concatenation of the notes with a transformation of the notes. So if we go back to Bach here, we can see we've got the notes and a transformation of the notes. But we're able to represent it really directly because we're working in higher order functions. And it also lets us talk about the awesome menagerie of cool canons that existed in Bach's day. So a simple canon, and we get that by choosing f to be this particular simple function, it says take the notes where the time is from some delay. So all it says is the first melody starts at 0, the second melody is delayed a bit, and they work well together. An interval canon has that symmetry in the other space that I mentioned. So an interval canon is translated in pitch, not in time. So you have the first melody at a certain pitch and the other melody that is higher or lower by a certain amount. There's some other, those are kind of easier ones to do. Mirror canon is really cool. So that's where you negate the pitch. So you can actually see just from this this little definition here, you almost see that single character. That's kind of what defines what it is. It just rotates the melody around the x-axis. A crab canon is the complement of the mirror canon because it goes backwards in time. Because in Bach's day, people mistakenly believe that crabs walked backwards. So it's rotated on another axis. And I think one of the coolest ones that must have been really hard to write for is called a table canon. So a table canon is a functional composition of mirror and crab. So the reason is that if you imagine two musicians seated at a table where they're reading that dots on a page, and each of them is playing what they see. So in other words, one is seeing it upside down, or they're seeing it upside down from each other. So you get that by rotating in both axes. So you can express a table canon, just literally functional composition right out of the box of mirror and crab. So before I get to Bach, I do want to reveal that Row, Row, Row Your Boat, that I discussed a bit earlier, has a canonical structure. So children often sing, and then a second group of children will sing the same melody after a delay, right? So here's what that sounds like. Second melody. So that's very carefully chosen, to be clear. It is not true that you can just take any melody and apply a canonic structure and get something that's cool, right? So the key is to searching the space of potential melodies and finding those ones that will work with an appropriate transformation. Machine learning could be one way to find it, yeah. Well, I think as maybe always with machine learning, the difficult bit of that would be defining what good sounds like, because you could naively kind of just say these two things harmonizing together, that's a good idea, but developing it so that the actual machine learning was able to generate something that was pleasing would be harder. But generating candidates that a human could listen to, I think that's quite plausible. So I'm just redefining Canon slightly to add a little extra tag so we know which notes are the follower and the leader. So let's get to Canone alla Quarta, the Bach piece. So the Canone alla Quarta, I said that finding canons was difficult. So finding this, I think, I wouldn't say this lightly, but is kind of a work of genius. So Canone alla Quarta is a canon that the transformation is actually a composition of 3 other transformations. Right? So the Canone alla Quarta function, the F that we choose to make it a canon, is a functional composition of a simple canon, it's delayed, a mirror canon, it's reflected, and an interval canon, so it's lowered. So all of those 3 simultaneously. So this is something that was, I guess you could say written, but you could almost say discovered by Bach, that there was this really interesting piece of music there. So I'm first going to play you the melody with just the bass, without the second melody, because it's pretty cool just on its own. So it's a pretty interesting and complicated thing. To find a melody that complex that would also work when you delay it, flip it, lower it, is really, really impressive. So I'm going to play that. I'm also going to do something a little bit different to display it to you. So here's both melodies together. That's Canone alla Quarta. But because it's in programmatic form, well, that's how I was able to display it. It's not very much code sitting at the bottom of the file using Quill, something else written by Sam, as it happens. Because we were in data form, because we were in a pure place where we could apply pure transformations, and we only do the side effects at the edge. So we can pump it to the speakers, we can pump it to the screen, we can do all sorts of other analysis. And we can also do things like change the key, right? So we can, if we wanted to work out, well, what would that sound like in minor and faster? So I think the first one I always think sounds quite like a period costume drama. That's kind of the picture in my head I get with the first one. Let's try the second one. It's more kind of like cop drama intensity, right? It's much tenser. Of course, again, not mathematically tenser, but just there's an association. Or maybe, I don't know, maybe faster tempo is actually something that's real, right? Because it matches a heightened heart rate or doing things faster. Cool. So there's a really famous quote by Charlie Parker that exists in various forms, which is that you should learn your scales, you should learn the chords, the notes, and then when you get up on stage, you should just forget all of that and just wail. So the idea is you need to have that background of theory in order to produce something interesting, but then you should, at the end, be just guided by your own instinct. So before I get to the end of the talk, I wanted to do a little piece to show you what it's actually like to kind of live code using this theoretical framework. And also to show you, I guess, so the weak claim of my talk is that using computation to represent music is interesting and illuminating to do, right? So I think that's fairly easily made. The more complex, the stronger claim that I would also make, that's probably a little bit harder to prove, is that the nature of music is computational. That unfolding, that idea of repetition and variation is not something that I'm putting on top of music from the outside. It's something that is inherent to the domain itself and existed, as you see by Bach's canons, long before anyone invented the computer. So a nice consequence of that is that when you're writing a piece and adding new notes and part, it's literally in both senses development. like software development and musical development. It kind of, your mind is processing the new transformations, the new parts as new things come along. So I want to demonstrate how that might work. Oops. So just turn it down a little bit. So I'm going to do a version of the piece In the Mood, if you've heard of it. So to start with, I've got almost nothing present. So I'll just evaluate this. So all I'm doing is playing a bass line of the 0 note of the scale over and over again. So if I start to write a melody, you can start to hear it come together. We could put a beat on it maybe. Maybe you could just slow it down slightly actually. Oops. I can see it. Now the problem. I don't actually want just the bass line. I want the bass line to play over my chord progression. So I need bass line to not be a series of notes. I need it to be a function. So I want to map bass line over 003-040, which is the blues, kind of 12-bar blues. And then what I want to do is, I guess, I want to make bass line a function. And I want to say, let's take this phrase, but we'll use a starting point as, well, actually, where pitch, comp, lower, lower. We want to lower it a bit. And then we're going to say where pitch is from the bass note. Oops. Just stop that and try to restart it. Oops. Let me just try rolling back that change. Oops. Like versioning is actually, oh, it seems to be have gone silent. I will just restart. Version control is a really powerful way of composing music because you can, you don't have to be as good in one moment because you can just use the power of accumulative change to gradually bring your decisions to bear over a long period of time. So it's actually quite useful. And the REPL is 49880. Cool, let's try it again. We might have a bit of a whoop as it starts up. Or maybe not. Whoa. Oh, wrong number of args passed to baseline. Right. So we don't want to map, we need a special map, map then, where we'll compose things together in time. Right. Let's try that then. No. All right, let me switch to a pre-prepared one. Cool. So what we've done here is, without making whatever mistake it was I just made then, we've turned baseline into a function and we're walking it through the chord progression. So we're doing map then baseline over root, root, 3, root, the 5th, because we're off by 1, because we're programmers, and then back to 0. We can bring the beat in as well, probably next time around. One of the really interesting things is, actually I'm gonna remove this tempo line, and maybe just listen when we get around to the start to see if you can hear what might be a little bit different. Right, so we're coming down to the last one, and then back. Right, very robotic. Why is that? Well, it's because we removed this swing here. So we can use our scale function with a 2/3 and 1/3 to actually stretch the first half of the beat and shrink the second half of the beat. So we now represent what swing is. Let's maybe make it a little bit faster. All right, we can make all these changes because it's in code. We control these things in a central way. All right, and so now what I'm going to do is, rather than playing the chords as an arpeggio, is just play them as playing chords. Yeah? So small variation in the domain, but it makes sense because we've represented things in a way that's close to the domain. Can't resist kind of giving this a go as well. Right? We'll switch back to the blues scale. Thanks very much.